Hello, this is the introductory lecture into Chapter 8 for Chemistry 121, fall of 2020. Chapter 8 deals with the relationships among the elements on the periodic table. This shows the periodic table together with the highest ground state electron configurations of the elements. Starting with hydrogen, 1 electron, 1s1. Helium, 2 electrons, 1s2. 3 electrons, 2 in the 1s, but 1 in the 2s. So this only shows where the highest and last electrons are being placed. Beryllium has 4 protons, 4 electrons, 2 in the 1s, but not shown. The other 2 remaining are in the 2s. Boron, 2s2, 2p1. Carbon, 2s2, 2p2. Nitrogen, 2s2, 2p3. Oxygen, 2s2, 2p4. Fluorine, 2s2, 2p5. Neon, 2s2, 2p6. Starting with the next element, sodium, 3s1. Magnesium, 3s2. Aluminum, 3s1, 3p. 3s2, 3p1. Silicon, 3s2, 3p2. 3s2, 3p3 for phosphorus. 3s2, 3p4 for sulfur. 3s2, 3p5 for chlorine, 3s2, 3p6 for argon. Starting with hydrogen, the subshells are filled in the order 1s, 2s, 2p, 3s, 3p, 4s, 3d, etc., etc. According to the type of shell being filled, the electrons can be divided into 2 categories. Representative elements, divided into multiple categories. Representative elements, those elements in this first 2 blocks here, P block elements. These last 6, the transition metals or the D block elements, the lanthanides and actinide series of elements. The representative elements, also called the main group elements, are in 1A, 2A, 3A, 4A, 5A, 6A, 7A. These have incompletely filled S and or P subshells and the highest value of N. In noble gas elements column in 8A, they have completely filled S and P subshells. Elements in the B grouping, 1B, 2B, 3B, 4B, 5B, all those. Incompletely filled subshells. These are sometimes referred to the D block transition elements. Lanthanides and actinides are called the F block transition elements because they have incompletely filled F orbitals. All the elements in this first column have an NS1 electron configuration, N referring to their row on the periodic table. These elements in the second column have NS2 electron configurations. 2s2 for magnesium, again, 3s2 for magnesium. Again, this chart only represents the highest and the last electrons. Column under boron is an NS2-NP1 general electron configuration. Boron, 2s2, 2p1. Aluminum, 3s2, 3p1. Gallium, 4s2, 4p1. Indium, 5s2, 5p1. Tantalum, 6s2, 6p1. Element 113, 7s2, 7p1. Elements under carbon have the NS2-NP2 designation. Carbon, 2s2, 2p2. Silicon, 3s2, 3p2. Germanium, 4s2, 4p2. Sin, 5s, 5p2. Lead, 6s, 6p2. Element 114, 7s2, 7p2. Elements under nitrogen, ns2, np3. Elements under oxygen, ns2, np4. Elements under fluorine, ns2, np5. And the elements in the very last right-hand column of the periodic table, noble gases, ns2, np6. These are generally D1 elements. These are D5 elements. These are D10 elements. Again, the last electrons here are going into and filling up your D orbitals. Here, these are filling up your 4f. These are filling up your 5s, 5f electron orbitals. So an atom with a certain electron configuration has 15 electrons. Without looking at a periodic table, what is the answer to the following questions? What is the ground state or non-excited electron configuration of the element? It has 15 electrons. 1s, 2s, 2p, 3s, 3p, 2 in the 1s, 2 in the 2s, 2, 4, 6 in the 2p. Of the 15 total we started out with, 2, 4, 6, 8, 10 have been accounted for. 2 in the 3s, and then 1 in each of the 3p. 2, 4, 6, 8, 10, 12, 13, 14, 15. So this should be a 3s2, 3p3 ground state electron configuration. The element should be classified as a p block element because the last electrons are going into your p orbitals. Is this element diamagnetic or paramagnetic? Since we have these unpaired electrons up here in your 3p orbital, this element is paramagnetic, i.e. it responds to the presence of a magnetic field. Let me see. So we have 1s2, 2s2, 2p6, 3s2, 3p3. Because this subshell is not completely filled, this is the representative element. Based on this information, we cannot say whether it is a metal or non-metal or a metalloid. According to Hund's rule, 3's electrons into 3p's have parallel spins, therefore the element is paramagnetic. We can use these electron configurations to represent elements that are cations, elements that are anions, or polyatomic anions. Those species that form cations have the noble gas configuration of the noble gas that is previous to them on the periodic table. Sodium has 11 protons, has 11 electrons. So 10 of the electrons have the electron configuration of neon. The 11th is in 3s1. Sodium, since it's in that very first column, it loses 1 electron. So the sodium cation has the same electron configuration as neon. Calcium, 20 protons, 20 electrons. It has the same electron configuration as argon, then 4s2. Since calcium is in the second column, it loses 2 electrons. It forms the calcium plus 2 cation. The electrons that are the outermost, highest electrons are in the 4s2 shell of calcium. Therefore, when calcium loses those 2 electrons, it has the same electron configuration as argon. Aluminum. Aluminum can lose up to 3 electrons. The most common thing for it to do is to lose 3 electrons. The highest electrons available for aluminum to lose are in the 3s2, 3p orbitals. Once Aluminum loses those 3 electrons, forms of aluminum plus 3, which has the same electron configuration as the noble gas immediately previous to it on the periodic table. So metals are atoms that lose electrons so that the cation has the noble gas configuration of the noble gas immediately previous to it. Hydrogen is a weirdo. Hydrogen can either gain an electron or lose an electron. If hydrogen gains an electron, there are reaction conditions where you can react a source of hydrogen by itself, just H, such that it gains an electron, becomes a -1 charged species. This has a 1s2, 2 electrons in the 1s orbital, has the same electron configuration as the noble gas to its right. Fluorine, its electron configuration is 1s2, 2s2, 2p5. When fluorine reacts, it's a nonmetal. It gains electrons. It gains 1 electron. That makes this electron configuration for the fluoride anion 1s2, 2s2, 2p6, or identical to neon. Oxygen, 1s2, 2s2, 2p4. To fill up this outer level, this takes 2 electrons. So oxygen -2 has 1s2, 2s2, 2p6, or Ne, the electron configuration for neon. Nitrogen, 1s2, 2s2, 2p3. When nitrogen reacts, it gains 3 electrons. It has 3 spaces available in the p orbitals to put those electrons. So when nitrogen becomes the nitride anion, has the electron configuration 1s2, 2s2, 2p6, or open bracket Ne, close bracket, the same electron configuration as the noble gas to its immediate right. So anions are atoms that gain electrons so that it has the same electron configuration as the noble gas to its right. So, as we've had talked about this from previous lectures, all these elements in this first column have or form a +1 charge. Why? Because they have 1 electron in the highest level. It's in the S level. It's an S1 designation. The elements in the second column can lose 2 electrons. Why? Because the highest electrons, those that are furthest away from the nucleus, there's 2 of them. They're both in an S level. Elements here in this column, the column under boron, can lose up to 3 electrons. So they have the S2 P1 designation. So they lose the electrons from the S, 2 in the S and 1 in the P, to form +3 ions. If we jump over here, now we're in the nonmetals. All these have a -1 charge because they gain 1 electron so that they have the identical electron configuration as the noble gas immediately to the right of it. So fluorine becomes fluoride anion, has the S2P6 configuration. Chlorine becomes the chloride anion, 3s2, 3p6, same electron configuration as argon. Bromine becomes the bromide anion, 4s2, 4p6, same electron configuration as krypton. Iodide becomes the iodine anion, 5s2, 5p6. Oxygen becomes the oxide anion. It gains 2 electrons. It becomes S2P6, the same electron configuration as neon. Sulfur, 3s2, 3p6, same as argon. Selenium, Se2 minus, 4s2, 4p6. Same number and electron configuration as krypton. Tellurium, telluride, Ste minus 2. 5s2, 5p6. Same electron configuration as xenon, and so forth and so forth. Elements in this column can form -3 ions. The nonmetals, nitrogen, phosphorus. Arsenic is a metalloid. Beneath that, we're getting into metals. Sometimes we are talking about elements, or we have to deal with those materials that are what are known as isoelectronic. You may have one element that has either gained or lost electron, but has the same electron configuration as something else that's a different species. This is isoelectronic. They have the same number of electrons and therefore the same ground state electron configuration. The sodium cation has lost one electron, 1s2, 2s2, 2p6. That is the same electron configuration as neon. But notice, the aluminum plus 3 cation also has 1s2, 2s2, 2p6. It lost the 3s2, 3p1 to generate the aluminum plus 3 cation. The aluminum plus 3 cation also has the same electron configuration as neon. Therefore, Na plus and Al plus 3 are isoelectronic. Fluoride anion, 1s2, 2s2, 2p6, has the same electron configuration as neon, which is also the same electron configuration as the aluminum plus 3 cation and the sodium plus 1 cation. So the sodium cation, the aluminum plus 3 cation, and the fluoride anion are all isoelectronic with one another, meaning that they have the same electron configuration. Oxygen, O2 minus, 1s2, 2s2, 2p6. Again, O2 minus oxide anion has the same electron configuration as neon. Therefore, O2 minus is isoelectronic with fluoride, the aluminum plus 3, and the sodium plus 1. Nitride, again, 1s2, 2s2, 2p3. It's gained the 3 electrons, 2p6. Again, 1s2, 2s2, 2p6 has the same electron configuration as neon. So sodium cation, the aluminum cation, the fluoride anion, the oxide anion, and the nitride anion are all isoelectronic with one another and isoelectronic with the noble gas, neon. When we have a cation that is formed from an atom of a transition metal, electrons are always removed first from the s orbitals. And once all the electrons, a maximum of 2, have been removed, then they start taking electrons out from the d orbitals. Iron, from your table and your chart, you should remember that iron can form multiple charge states. Iron can form +1, +2, and +3 charge states. Well, how many electrons are available for iron to lose in the highest orbital? The 4s2. D orbitals come next. So to generate the iron plus 2 cation, it loses these 2 electrons from the 4s. So the iron plus 2 cation has argon 4s20 3d6, or argon 3d6. The next electron that iron loses is out of this d orbital here. If it loses an electron from orbitals that are lower than this, it starts taking away from the argon electron configuration, which is very stable, which it doesn't want to do. So the iron plus 3 cation, argon 4s0 3d5, or argon 3d5. Manganese has the electron configuration for argon 4s2 3d5. Manganese can form +2 or +4. So if manganese loses the 2 electrons to become manganese plus 2, the first electrons it loses are the 4s. So argon 4s0 3d5 or argon 3d5. Manganese can form a plus 4 cation, again, losing electrons out of the d orbitals. Harkening back to the model that we have, at least initially, of the element itself. You can think of the nucleus as a ping pong ball. Concentric circles drawn around the ping pong ball at specific distances away from the nucleus represent a picture of energy orbitals. Not an exact picture, but a representation. Okay. Don't have that. Okay. We can draw pictures. Here is our nucleus. These concentric, what should be circles, but are not, represent electrons filling up from lower energies to higher level energies. The farther out or farther down we go on a periodic table, you have more and more of these electrons circling around the nucleus. So I'm going to draw E1, E2, E3, E4, something like that, representing all the various electrons. These, the electron, the pull from the protons in these electrons is, in these outer, further away electrons, is not as great as we would expect it to be. Because these inner electrons can act as sort of a shield or a block, such that the outer electrons, E3 and E4, don't feel as much pull from the protons in the nucleus than we would expect them to. So they don't feel the full nuclear charge, they feel an effective nuclear charge. So this is the positive charge felt from an outer electron due to the presence of these inner electrons basically shielding these outer electrons. So the effective nuclear charge is equal to the atomic number of protons, minus some value, sigma. Sigma is a number between 0 and the atomic number. It's defined as the shielding constant. So if we define an electron here, since there are no electrons beneath it closer to the nucleus, this has a 0 shielding constant. So E1 and E2, since there are no electrons closer to it than that, E1 and E2 experience 0 shielding due to any inner or closer electrons. Electrons 3 and 4, the Z effective is some value less than the atomic number, because electrons E1 and E2 basically shield electrons 3 and 4. So for most elements, for most lightweight elements, the effective pull that electrons 3 and 4 feel from the protons in the nucleus is almost equal to the atomic number of protons minus the inner number of electrons or core electrons. So for electrons 3 and 4, their effective nuclear charge would be the atomic number minus 2, these 2 electrons, E1 and E2. How large or small that is depends on how effective E1 and E2 shield the nucleus from these outer electrons. So if we look at sodium, it has 10 electrons. Its electron configuration is 1s2, 2s2, 2p6, 3s1. We have Z as an atomic number. How many protons we have in a nucleus? 11. How many core electrons do we have? Here. The outer electron, that last electron, is there. So this 3s1 electron is being shielded by the 1s2, 2s2, and 2p6. So these are the core electrons. There are 2, 4, 10 core electrons. Therefore, the effective field that this one electron is feeling is 11 minus 10, or an effective field of 1. So here's the radius for a sodium ion, for a sodium atom. Magnesium, 12 protons. So for magnesium, this is sodium. Here we have magnesium. One S2, 2s2, 2p6, 3s2. Again, for magnesium, 12 protons, 12 electrons. We have 2, 4, 10 core electrons protecting these outer 2, 3s electrons. But notice, you have more electrons being shielded by the same number of inner electrons as you did here. So the effective pull that these outer electrons experience is greater than it does here. Here you're spreading out that pull over 11 electrons. Here you're spreading it out over 12. So the radius here is 160. So the shear, or the portion of the attractive force that's experienced by this outer electron, is not as great as it is on these two, because this is dispersed over more electrons. The aluminum. Excuse me. The effective pull here is that you still have the same number of core electrons. But the number of electrons that are being distributed across is 12, but you also have one more proton pulling on the electrons. So since the addition of that additional proton in the nucleus, these electrons are pulled closer than they would necessarily be here in the 3s1 system. Therefore, the radius is smaller. Aluminum. We have, again, still 10 core electrons, but we have, again, compared to magnesium, added another proton in. That proton, you're still only shielding these with 10 core electrons. You have 3 electrons, the S2p1 electrons, S2p1. Those 3 electrons are feeling the pull from 13 protons. Therefore, the distance is smaller. So as we start going from left to right across the periodic table, you were told that size decreases. You were told that essentially, because these outermost electrons are feeling the pull of more protons. This is that concept put into some sort of mathematical picture for you. So effectively, the effective nuclear charge increases from left to right across the periodic table, and increases top to bottom. Sorry, this should be going the other way around. Increasing the effective, atoms get smaller, left to right. This should be the other way around. It should be atoms get smaller, bottom to top. My apologies. Increasing Z effective here. So we know why it decreases left to right, because we've got electrons that are being attracted due to more protons. But why does it increase bottom to top? Well, if you're going from bottom to top, why does the increase net effective? Just as simply because you are decreasing the distance away that the outer electrons are from the nucleus. You're decreasing the core electrons. You're decreasing the number of protons. So since you're decreasing these core electrons, here compared to here, the effective pull on those outer electrons increases. Physical properties of atoms or metals or mixtures of elements are affected by their physical properties. Density, melting point, boiling point can be attributed to how big or small the size of the atom is. But sometimes atomic size is difficult to define. The electron density in an atom extends far beyond the nucleus. But we need to remember that the atomic size is thought as the volume contained about 90% of the electron density around the nucleus. But where's the other 10% come into? Doesn't that affect how big or small an atom is? The answer is yes. If you need to be more specific, the size of the atom is defined in terms of its atomic radius. The atomic radius is defined as 1/2 the distance between the two nuclei in adjacent metal atoms or in a diatomic atom. For diatomic molecule. For atoms that are linked together in this three-dimensional network, the atomic radius is simply 1/2 the distance between the two nuclei in neighboring atoms. So the radius would be 1/2 this distance, or the distance from there to there, or the distance from there to there. That would be the radii. For elements that exist as covalent diatomic molecules, H2, O2, N2, O2, Cl2, whatever. Again, for covalent compounds, the distance is 1/2 the distance between the nuclei of the two atoms in any particular molecule. So here you have the metallic elements, here you have diatomic elements looking at their covalent radiuses. This is figure 8.5 on page 355 of your textbooks. It shows atomic radii of many elements according to their position in the periodic table. Periodic trends are hopefully clearly evident. If you look at these second row elements, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, as you go from left to right, the size of these elements gets smaller. The ionic radius, decreases. Again, the electrons that are being added are being drawn closer because as we go from beryllium to boron, you're adding more protons to the nucleus. Boron to carbon, one more. Boron to nitrogen, one more. Nitrogen to oxygen, one more. Oxygen to fluorine, one more. Fluorine to neon, one more. So as we go from left to right, the more protons there are in the nucleus, the effective charge increases as we go from left to right. with any vertical column. Atomic size increases. So the distance between two potassium atoms is less than the distance between two rubidium atoms, because those electrons are being placed in larger and larger orbitals that are further and further away from the nucleus. So referring to the periodic table, arrange the following atoms in order of increasing atomic radii. So which is largest? Is it phosphorus, sulfur, silicon? Phosphorus, silicon, nitrogen, silicon, phosphorus, nitrogen, nitrogen, silicon, phosphorus, nitrogen, phosphorus. How do they range in size? How can we arrange them in increasing order of size? So we look at their general positions in the periodic table. Nitrogen and phosphorus are not in the same horizontal rows. Nitrogen and oxygen are. Phosphorus and silicon are in the same rows. But nitrogen is not. Nitrogen is in the row above it. So the first we can assume that since nitrogen is in the row above both phosphorus and silicon, it's the smallest of the three. Then the next thing we have to look at is, where do phosphorus and silicon relate to one another positionally in their row? Nitrogen is in the row above phosphorus and silicon. Therefore, nitrogen is the smallest, but where do phosphorus and silicon sit with respect to one another? If we look at their positions on the periodic table, phosphorus is to the right of silicon. Since it's to the right, it's smaller than silicon. Therefore, the correct way to arrange these guys is nitrogen, phosphorus, and silicon. When we're talking about radii, we need to be careful. Are we talking about the radii of the neutral species, or are we talking about the radii of the ionic species? So we can have the radius of the cation or the radius of the anion. The physical properties of sodium metal are radically different than sodium cation. Sodium metal will react explosively and detonate when in contact with water, but the sodium cation doesn't do anything. It just sits there and laughs at you. The reactivity of potassium, rubidium, and cesium, as this goes up, the reactivity of these guys increases. But potassium, rubidium, and cesium cations, they are relatively inert when in aqueous solutions. Fluorine, chlorine, bromine, and iodine are basically very reactive. The chloride anion, the bromide, and the iodide have very different reactivities than fluoride atom by itself. The chloride atom, the bromide anion, bromine atom, the iodide atom. So these species are different from one another. They have differing chemical and physical properties. So when we start with the neutral species that form the anions, when a neutral atom is converted to an anion, a change in size is expected, because if you're going from the bromine to the bromide, you're adding an electron in, but the atomic number, the number of protons, does not change. So the effective nuclear charge remains the same. But since you're adding in an additional electron, the electron repulsive forces, the repulsive forces between electrons, is increasing. Therefore, the size increases. It almost doubles by adding that one electron in. So from fluorine to fluoride, you see it maybe somewhere about doubles. Chlorine to chloride definitely doubles. Bromine to bromide, it doubles. Iodine to iodide, it doesn't exactly double. Well, it looks like it may double. It's close to doubling in its size. So the addition of those electrons into that shell causes the electronic repulsion to increase, making the electrons push farther away from one another. Therefore, the anion is larger than the original neutral species. If we're starting out from these neutral elements and we're losing electrons, lithium loses one electron, becomes a lithium cation. Sodium loses one electron because the sodium cation. Potassium loses an electron, becomes the potassium cation. Rubidium and cesium. Again here, removing an electron from an atom reduces the electron-electron repulsion, but the nuclear effective pull remains the same. So the electron cloud shrinks. Therefore, the size of the cation is smaller than the original neutral atom. So we can see this is, I don't know if this is exactly to scale, but we can see in some respects what happens to the size of the cation and the anion when it's generated. Starting out from the neutral lithium, from the neutral fluorine. Lithium donates the electron to fluoride. Lithium has the electrons in lithium feel a greater effective pull. Therefore, the size gets very much smaller. Fluorine puts that extra electron in, the electron repulsions are larger, therefore the fluoride anion becomes larger. So the cation is always smaller than the neutral atom from which it is formed. The anion is always larger than the neutral atom from which it was formed. This is figure 9.9, which shows the radii of the ions derived from hopefully familiar elements according to their position on the periodic table. Again, notice as we shift and move about elements on the periodic table, we see generally as we go down periodic table, the elements, the ions get larger. Again, just general trends. 140 for oxygen, oxide 140, sulfide minus 184, selenide 198, telluride minus 211, fluoride 133, chloride 181, bromide 195, iodide 220. Again, you're looking at these electrons going into further and further orbitals that are larger, take up more space, more electron repulsions, they get larger. And as we go down, the elements get bigger, the ions get bigger. Again, same general trends as we would see when we're talking about the neutral elements. Within the d elements, there's a radical change that occurs between where electrons are and where they lose out of. Therefore, you will see varying charges as these and varying sizes as these things go across the periodic table. For those things that can form multiple charges, we see that the iron plus 3 is smaller than the iron plus 2. The iron plus 2 is this outer sphere. The iron plus 3 is defined by this inner boundary. The copper plus 2 is this inner sphere. The copper plus 1 is defined as this outer sphere. So that follows as we should think it should. So in each of these pairs, indicate which of the two is larger. Nitride or fluorine. That should be fluoride, F minus 1. Magnesium cation or the calcium cation. Magnesium plus 2 or calcium plus 2. Iron plus 2 or iron plus 3. Well, let me see, we got N minus 3 or F minus 1. Should be F minus 1. N minus 3 is 171. F minus 1 is 133. So of these two, nitride anion should be the larger of the two. Magnesium cation or calcium cation. Here's magnesium, 78. Here's calcium. Again, calcium cation is beneath magnesium on the table, therefore it will be larger than the magnesium cation. Iron plus 2 or iron plus 3. Again, iron plus 3 is represented by this inner black circle. Iron plus 2 is represented by the space that's designated by the purple sphere. So the iron plus 3 is smaller than the iron plus 2. So N minus 3 and F minus are isoelectronic, both containing 10 electrons. But N minus 3 has only 7 protons and F minus has 9. The smaller attractive force exerted by the nucleus on the electrons results in a larger N minus 3 ion. Number B, both magnesium and cation belong to the group 2A, on earth metals. Therefore, calcium plus 2 ion is larger than magnesium because calcium electrons are being lost from the N equals shell than our magnesium electrons in the N equal 3. Both then Fe plus 2 and Fe plus 3, both ions have the same effective nuclear charge, but Fe plus 2 has one more electron, 24 electrons in Fe plus 2 versus 23 electrons for Fe plus 3. Therefore, the greater electron-electron repulsion creates the Fe plus 2 having a larger ionic radii. Next concept, ionization energy. Ionization energy is that minimum amount of energy that's required to remove an electron from a gaseous atom in its ground state. We write this as the representation for an ionization energy. The ionization energy is the amount of energy that needs to be added to it such that an electron is released. The element is in the gaseous state. So the I1 is the first ionization energy. Since this costs energy, this is an endothermic process. You have to put in energy respectable to or proportional to this I1 value to get this element to release an electron. I sub 2 is that amount of energy that you have to put in to cause this ion to remove another electron. Second ionization energy. Third ionization energy, I sub 3, the energy that has to be spent in removing a third electron. So this sequence shows us that as we go through this series, the ionization energy that it should take to remove the first electron is going to be less than the second, and the second is going to be less than the third. Why? Here you have a neutral species. You're removing one electron, not necessarily that difficult to process. However, when you're looking to remove that second electron, you're already looking to remove it from an electron deficient species. Therefore, you have to add extra energy to remove that second electron. The third ionization energy. This is a very electron deficient species. You're looking to remove an electron from something that has a +2 charge. Not necessarily a very easy thing to do. So the third ionization energy is generally greater than your second ionization energy. How large this value is depends upon how tightly that electron is held in the atom. The larger the value for I1 and I2 and I3 are, the more energy it takes to remove the electron. Term X is an atom that represents any element, and E is the electron that's being removed. When an electron is removed from any species, the repulsion among the remaining electrons decreases. Therefore, the size decreases. If that size decreases, then those electrons are being held closer to the nucleus, not only because the repulsive forces are less, but the effective nuclear charge increases. So this is table 8.2, and it lists the first ionization energies of the first 20 elements. So hydrogen down to calcium. Since ionization energies are endothermic processes, therefore by convention, since energy is absorbed by the atom or ion, the ionization process has a positive value. Thus, ionization energy is always shown as a positive number. So hydrogen and helium, why are these ionization energies so large? Well, where are the electrons we're looking at to remove in hydrogen and helium? Those electrons are in that 1s orbital that is the closest orbital with respect to the nucleus. Lithium, you're in the 2s orbital. That's where you're looking to take that first electron out. It's still relatively close, but not as close as these inner electrons are. Remember, this electron here is in the 2s1. It's being shielded by the 1s2 electrons here and there. Beryllium, boron. We can see that there is a large difference between the first ionization energy and the second ionization energy. Here, the first ionization energy, you've already removed one electron. This lithium cation now has the electron configuration of the previous noble gas. Those electron configurations are extraordinarily stable. So to remove that second electron, you've really got to beat on it. It's almost impossible to get to the lithium +2 cation. Beryllium, same thing. As you remove that first electron, becomes the Be+1. To get that second electron to become Be+2, you got to kind of beat on it. We see as we go down, generally we see general increases in the ionization energy. We're also noticing that we're going from left to right across the periodic table. We're adding in more protons to the nucleus. So as we go down, generally we're seeing increasing values for the first ionization energies. So here's how they change with respect to one another sequentially on a map. So the variation of the first energy with atomic number. Note that the first ionization energies of elements in a row increase with atomic number. So 1 to 2, 3 to 4, 5 to 6, 7, 8, 9, 10, jumps down 11, 12, 13, 14, 15, 16. So we see that the effective nuclear charge holds more electrons, held the electrons tighter, and create a higher first ionization energy. Please also note that those peaks that correspond to the noble gases. The higher ionization energy of the noble gases stems from their larger effective nuclear charge, highest ratio of protons to electrons. This is one of the reasons that these things are most stable. You've got in helium, neon, argon, krypton, xenon, and radon, you've got the maximum amount of pull on the electrons that are orbiting that nucleus of all those elements in that row. At the bottom of the chart are the group 1A elements. They have the lowest first ionization energies. Each of these metals has one valence electron, which is shielded rather completely and nicely by their filled inner shells. Consequently, energetically, it's easy to remove that electron from this alkali metal to form a +1 charge. So these +1 charges of these cations are all isoelectronic, i.e. have the same number of electrons as the immediately previous noble gases. Also notice that your metals down here generally have lower ionization energy compared to nonmetals. Ionization energy of your metalloids here. Generally fall between those of metals and nonmetals. So for any given group of elements, those elements in a vertical column, ionization energy decreases with increasing atomic number. However, elements in the same group, row, have similar outer electron configurations. However, as the value of the atomic number increases, so does the average difference between the electron and the nucleus. It makes a weaker attraction, so that it becomes easier to remove that first electron. As we move from element to element down any column, even though the effective nuclear charge also increases in the same direction, this means that the metallic character of the element in the vertical column increases from top to bottom also. So here are our filled shells. So as we go from bottom to top, we have an increase in the first ionization energy. As we go from left to right, we have an increasing first ionization energy. So let's finish this lecture with answering these questions, and then we'll pick this up on Monday, November the 2nd. Which atom should have a smaller first ionization energy, oxygen or sulfur? Which atom should have a higher second ionization energy, lithium or beryllium? Well, let's look at oxygen or sulfur. Where are they with respect to one another on the periodic table? Well, they're in the same vertical column, but are they in the same row? No. They are in different rows, but the same vertical column. So the first ionization energy. These electrons here are further away from the nucleus because they're in a lower row. So the electrons here are further away from the nucleus, feeling much less effective pull from the nucleus. These electrons, the outermost electrons here, 3p1, 3s2, 3p4, those electrons are being shielded by more these outer electrons are being shielded by more electrons than are present here. even though these are in two different rows, there are many more protons pulling these electrons. We're talking about the distance out that these electrons are from this nucleus here, and the number of electrons that act as shielding agents, shield the outermost electrons of the sulfur to a greater extent than the electrons in the oxygen. So the ionization energy for sulfur, first ionization, should be less than oxygen. Let's look at beryllium and lithium. Are they in the same vertical row? Same vertical column? No, they're not. Are they in the same horizontal row? Yes, they are. They're not in the same vertical column, but they are in the same row. Where are they positionally with respect to one another? Lithium is on the far left, beryllium is on the right. So as we go from left to right across the periodic table, ionization energies go up. So are we talking about the first ionization energy? No, we're talking about the second ionization energy. How many electrons does beryllium have to lose? Well, 2. But notice that beryllium, if it loses 2 electrons, it becomes beryllium 2 plus, has the same electron configuration as neon. Lithium, if it loses 2 electrons, it doesn't even have the electron configuration of neon. It has, let me see, here's lithium. It has the same electron configuration as fluorine. What's more stable, neon, or something has the electron configuration of fluorine? Something that has the electron configuration of a noble gas, neon. So the lithium plus 2 should have a much higher second ionization energy. So oxygen and sulfur are members of the same vertical column. They have the same valence electron configuration, Ns2Np4, but the 3p electrons in sulfur are so much further away from the nucleus and experience less nuclear attraction than those electrons in the 2p. Therefore, we predict that sulfur should have a smaller first ionization energy. So again, from the beryllium, it can lose the second electron easier than the lithium, because the lithium, it would have to be going down into the previous electron configuration. We'll stop here, and then we'll pick this lecture up on Monday. Have a good weekend. See you later.